students. We are going to discuss about the topic vector control of induction motors by Aniruddhan. Now we are going to see the basic principles of vector control. In separately excited DC motor, the both field flux and electromagnetic torque can be controlled independently by varying field current and armature current respectively in the machines, which is the field current can be controlled by field flux and armature current can be controlled by electromagnetic torque. Similarly, in AC motor, which is an induction motor, there is only one current, and this current is a stator current, which produces both flux and torque in the same machine. So, in AC motor, by using normal control techniques, independent control of torque and flux is not possible. So, we are using the vector control technique, which is the field orientation control. In vector control, an induction motor is controlled under the all operating conditions to get performance similar to a separately excited DC motor. The stator current IS of an induction motor can be resolved in two components. One is flux producing component, another one is torque producing component. Flux producing components can be represented by IM and torque producing can be represented by IW. If we are able to control the IM and IW, which is flux producing component and torque producing component, independently, the flux and torque can be controlled independently. In vector control, we are controlling IM and IW independently. There are three stator currents in three-phase induction motor, and they together produces the required flux and torque inside the machines. To control the torque and flux independently, we transform three-phase stator currents, which is IA, IB and IC, into two-phase current by using ABC, which is Clark transformations, and by using ABC to DQ transformations, also called as a Park transformations. Now the two-phase currents are flux producing components and torque producing components. The two types of vector control are direct vector control and indirect vector control. There are two control approaches of AC drive, which is a scalar control, and the scalar control is the term which describes a similar form of AC motor control by adjustable magnitude of stator voltages frequency in such a way that the air gap flux is always maintained at the desired values at the steady state. In vector control, the machine's current and the voltage space vectors transformations of a three-phase speed and time dependent systems into a two-coordinate time variant, which is effective in pulse width modulation pattern generations. Now we can see the scalar control versus the vector control. In scalar control, simpler form of motor, but in the vector control, the complex mathematical module and good steady state performance, a precious control of AC motors, poor dynamic responses, excellent dynamic responses in vector control, and the low performance drives and high performance drives. And scalar control has high power dissipation, which is compared to vector control, it has low power dissipations. An analogy with DC motor control, there is close parallel between the torque control of a DC motor and vector control of an AC motor. The AC motor field flux produced by the field current is orthogonal to the armature flux produced by the armature current. Because vectors are orthogonal, they are decoupled. The field current only control the field flux and the armature current only controls the armature flux. We are see in the beginning. In analog with the DC motor, the DC motors like the performance can achieve with an induction motor if the motor control is considered in synchronously rotating referencing frame, which is DE minus QE, while sinusoidal variables appears as the DC quantities in the steady state. With vector control, IDS is equal to IF. In IDS in induction motor and IF, which is the field current in DC motor, and IQS in induction motor, which is equal to armature current in the DC motor. And there is a principle of vector control. The basic conceptual implementation of vector control is illustrated in this diagram, which is different between control and the machines by the machine terminal. Control side is an inverse transformation, machine side is direct transformations. The vector control implementation principle of the machine, which is D minus Q model. The principles of vector control: the motor phase current IA, IB and IC are converted into IDS and IQS in the stationary reference frame. These are converted to be synchronously rotating reference frame, which is D minus Q currents and IDS and IQs. The control to inverse transformation is performed in synchronous D minus Q to the stationary D minus Q reference frame, which is D star minus Q star to A star, B star and C. And the time variant coordination transformation ABC to alpha beta, which is also called as a Clark transformations, and alpha beta to DQ is also called Park transformations. And Clark transformation 2 coordinates time variant system, and the Park transformation 2 coordinate time variant system. And by using this diagram we are discuss the Clark transformations. There are three phases, which is ABC quantity. It's rotating in the 360 degree, and this is the voltage, and ABC axis is displayed by 120 degree. Each we need to do convert this three phase into two phase quantity, but in a stationary reference this is the alpha beta reference in stationary. We are already discussed, which is AB to alpha beta is also known as Clark transformation, and alpha beta to DQ is in the Park transformation. We can mathematically express the Clark transformation, which is IS alpha is equal to IA and IS beta is equal to 1 by root 3 IA plus 2 by root 3 IB. In inverse Park transformation, voltage transformation that modifies the voltage in DQ rotating reference in the frame into a two-phase orthogonal system, which is we can mathematically express in the form of Vs alpha reference is equal to Vd reference cos theta minus Vsq reference sin theta, which is similarly Vs beta reference. In vector control type, there are two approaches. One is direct field orientation control approaches, and another is indirect field orientation control. Direct field, the rotating angle of the IQS vector with respect to the state of flux is being directly determined, but in indirect field it can be determined by indirectly, such as measured in slip speed. And the field orientation control and direct field orientation control, the field angle is calculated by using the terminal voltage and the current or Hall sensor or flux sense windings. We can express in the block diagrams. The ISQ reference and ISD reference, which is goes in the P1 and P1, and go to Park transformation and Clark transformations to the pulse width modulation, and it's get into the three-phase inverter through the AC motor. The same process is done. And there are the salient features for the vector control, which is the transient response will be fast, because due to the torque controlled by the IQ system affects flux. Automatic limits operations to the stable region. Vector controls allow for the speed control in all four quadrants without the additional control limits. And conclusions, which is the more computational efforts on high speed processors are suitable for this vector control. And another one, field orientation control AC machines thus obtain every DC machine advantages. And field orientation control used in the high performance drives where oscillations in air gap and flux linkages are inalterable. Example, robotics, actuators, centrifuges, servos, etc. Thank you.